Given that copper has an atomic mass of 64 grams per mole, a density of 8.94 grams per centimeter cubed, Young's elastic modulus of 1.17 times 10 to the 11th newtons per meter squared, and assuming a crystal lattice structure, 5 questions. What's the mass of a copper atom? The interatomic bond length, the interatomic bond stiffness, the angular frequency, and the speed of sound in copper. Get also Avogadro's number here, number of particles per mole, and this cubic lattice structure means that the atoms are in rows and columns, and they stack right on top of each other. The distance between centers, interatomic bond diameter, would be the same as the diameter, and they fit in a cube. Each one of these spheres fits in a cube that has all 3 dimensions of d, the interatomic bond length. So I'll pause the video, solve for these 5 things, and then I'll answer them. Here's a solution to these questions. The first one is just simple chemistry, the mass of an individual atom, given the atomic mass and Avogadro's number, one can determine the mass per atom. The next one, we were told that we're going to assume that there's a cubic lattice structure. In reality, copper is actually a face center lattice structure, but given this assumption, it's saying that these atoms are packed just in line, in a row, and in a column, and in height, and they're just kind of packed in these cubes one after the other, and they're lined up. So this atom here, this spherical atom fits in this cube, next to this cube, next to this cube, and it goes in the board and then straight up. And so the volume that one of these cubes takes up is both the diameter of this atom, is also the distance between the centers of the atoms. So this cube has the volume of d cubed. So we were given the density, we know the mass of an individual atom, we could turn in the volume of an atom, and so solving is the cube root of this equation, and we can solve for that, and we get the diameter of an individual atom, copper atom, being this, assuming that it's cubic lattice. Actually, there's very few that are, but that was the assumption I gave you for this problem. Next question was the bond stiffness. From the previous video, one thing to remember is that the change in length of a part due to a force is related to 4 things. It's the force, the length of it, the cross-sectional area, and Young's modulus. And so for an atom, we know that the length of an individual element is this d, and the cross-sectional area would be this bottom surface right here. So that's just d squared. So the area is d squared, and y, we get this. We also know stiffness is the derivative of force over length. This we're assuming is linear. For this case, a small deflection, so df dl and f max over delta L. We can kind of see from here that if I had f, to put the dl down here, that f over delta L equals dy. So the interatomic bond length times Young's modulus. In solving for this we can get the interatomic bond stiffness. So that's this stiffness between individual atoms. Okay. Next one was angular frequency. So angular frequency is we now have a mass and a stiffness. So how fast does this vibrate? Well, the stiffer it is, that'll make it vibrate faster, and the less mass it is, that'll make it vibrate faster, or more mass makes it vibrate slower. And angular frequency is the square root of a stiffness over a mass. So we know the stiffness, we know the mass of the atom, and often and using SI units, we're going to have newtons, and we're have to do some conversions. And probably the most handy ones to remember, is I highlighted here, is we know force equals mass times acceleration. In the SI units, a unit of force is a newton, and a typical unit for a mass is a kilogram. And acceleration is a distance per time squared, so meter per second squared. So it's all, and for the SI units, the newton is defined such that 1 newton is a kilogram meter per second squared. So this is a very common thing we're used to do, and we can cross out our units here and do all our check. So we get a newton is a kilogram meter per second squared. From here, we just end up with it's unitless on the top, which radians is a unitless number as well. So it's a radians per second, because there's nothing on the top, and we got second squared under the square root. So radians per second is my units for angular frequency. And the next is speed of sound. So the speed of sound is so these individual ones are vibrating at this many radians per second, and that message is being passed one to another. The longer the distance, the higher the velocity, the higher the velocity that frequency passes along. So the velocity is just the frequency that vibrates times the distance that's each vibration is transmitted. So the velocity of speed and sound is just this angular frequency times my interatomic bond length, which is here. So there's my speed of sound in copper with these assumptions. Given this problem, the next problem is if I put 10 Newton axial pulling force on a bar which is made of this copper, and the bar is 5 meters long and has a square cross section where each side of the cross section has 0.02 meters. What's the actual deflection? How much does this stretch? And I want you to try to solve it two ways. One, using what we've learned about interatomic bond length and bond stiffness, and just consider these to be millions and millions of atoms being stretched. That'll give you the answer. The other way is to use our 4 terms we know to see the answer. Compare them, and you can check yourself. So pause the video and then solve it. Looking at this bar as a composite, one can determine the change in length using our formula with our 4 variables. The force and length, those are both proportional to change in length, and inversely proportional are the cross-sectional area and Young's modulus. And so our force is 10 newtons, our length 5 meters, cross-sectional area is 0.02 and 0.02, and Young's modulus is this. So we simply can solve for that entire bar in one shot, and this is the deflection for 10 newtons. Another way we could do it is to consider that there's lots and lots of atoms, these little atoms here. And so if you think about one layer of this, I have as many atoms. We know the length of so we know the d, the length of each little atom, and there's lots of them stacked along this side and lots of them stacked along this time. And there's a spring connecting that to the next sandwich layer, and there's lots and lots of all these atoms. So we can find out these springs are all in this first layer. They're all in parallel, and then there's lots of different cuts in there, and each one of those is in series. And so we can solve for the deflection looking at the stiffness of an individual atom. So first, to find how many atoms along a side, we know how long the side is, and I know what's the length of this atom, the diameter of this atom. So just taking the simple ratio, I find out that there's this many atoms along each side here. And for this, to find how many springs there are, going from this first sandwich layer of atoms
this next sandwich layer of atoms, I'm going to have this many atoms, springs on this side, that many springs on this side, so there's multiplication of those, so that's squared, this number squared, so I have this many atoms or springs essentially in each cross section. And these, when I take this first layer of atoms and the second layer of atoms and I pull on it, I have all this number of springs that all see the same deflection. And if they all see the same deflection, they're in parallel. So the stiffness of an individual one, I'm going to have this many of those springs all acting with the same deflection. So I would add up springs in parallel. You just add up the stiffness of all of them. So I have this many of them. So that's the stiffness of an individual spring. Oops, newtons per meter times that many springs in one layer. So this is the stiffness. 2.07 times 10 to the 17 Newton per meter. That's the stiffness of this one layer of springs. And then I have all these different sandwich layers, all these layers along this whole 5 meter length. And so these are all these layers. The spring, it has the same force acting on each one of these sandwich layers. These 10 newtons. So these springs are in series, as opposed to this in parallel. And for springs in series, the stiffness of the total is 1 over the total stiffness there is 1 over the stiffness of the first spring plus 1 over the stiffness of the second spring, and keep adding up through all the springs. Now it's for this design right here, where every single spring has the same stiffness, then I essentially I have as many springs as there are layers here adding this up. So I need to find out in this 5 meter length how many of these atoms there are. And so that's just the length divided by the diameter. So there's 2.19 times 10 to the 10th layers, which is the number of springs in series. So since these springs are all the same, of this stiffness, that layer of springs, I'm going to have the total is just going to be, I'm going to have this many of those springs in series. So that's the number of series times the stiffness of each layer. And if I just rearrange that, I get the total stiffness then of all the spring is the number of layers, the stiffness of each layer, which is this, divided by the number of springs in series. And I can solve for that right here. So this is the total stiffness of this bar then. And I know stiffness is the derivative of force versus length, and delta force over length, and delta force is the maximum force minus 0 over change in length. Rearranging this, I can solve that the change in length is the force over the stiffness. My force is here, my stiffness I got from right here, and again I get the same answer as I did looking at it as a composite.